Right, here we have the linearized equations of lateral motion. We have a 4x4 state space representation. In the original format, it's not in the standard form because it's got a matrix E at the front here. And we have 4 variables associated with lateral motion, which are side slip velocity, roll rate, yaw rate, and roll angle. We can use the inverse matrix, e to the minus 1, to multiply by A to simplify this down to standard form, which will then give us this expression here for the A matrix. And so now the standard equations are written in the standard state space format. From here, we can extract the roll mode and Dutch roll mode parameters. To extract the roll mode, we go for this parameter here, which is the 2,2 element, and for the Dutch roll element, we pick up 4 parameters because it's a second order system, which is that parameter there, that one there, this one down here, and that one there, to form a 2x2 matrix. Then work out the eigenvalues, then compare with a standard second order system equation. So just to recap, this will give us the roll mode, and these 4 parameters put into a little matrix, work out the eigenvalues, will give us the Dutch roll mode.
Okay, we're back again. This time we're doing the approximations to the roll mode and Dutch roll mode. So the roll mode and Dutch roll mode, they come from the lateral dynamics. And in the lateral dynamics, we again have a 4x4 matrix, which has V, the velocity, side slip velocity, P, the roll rate, R, the yaw rate, and phi, the roll angle. And again, it's just a certain limited number of parameters which give us the ability to extract the roll mode and the Dutch roll mode. So the roll mode is particularly easy. It's just a 2,2 elements. The roll mode is actually equal to p hat. So we just extract the minus p there, and the roll mode will be p hat. So that one is very simple. So if we did this particular one here, so we'd go to this number here, so it's minus 9.99. So the roll mode would be 9.09. The time constant, this is a pole, remember. So the time constant is 1 over the pole, which would be 1 over 9.09. So that would be the pole, that would be the time constant. So next one to move on to is the Dutch roll mode. Now the Dutch roll mode comprises of using it's a second order mode, so it's going to be modelled by this type of equation here. And we're going to use those 4 parameters to extract the Dutch roll mode. So this is quite similar to what we did in the previous example. So we could call that parameter there, say A, this one here B, that one there C, and that one there D. So we called those A, B, C, D. It now becomes, we can extract from the 4x4 a simpler matrix A, B, C, and D. Once you've extracted the 4x4 down to a 2x2, we can then go and work out the eigenvalues of this, which again is the same type of thing we did before, because Si minus A equals 0, assuming that this is the A. So then we'll get S minus A minus B minus C, S minus D as our 2x2, and then this will give us, can work out the determinant of this now to get the eigenvalues. It's going to be this times this minus this times this. So it's going to be S minus A times S minus D minus BC equals 0. So it's going to be that times that minus that times that. So 3 minuses gives a minus. And we can expand this out to give us S squared minus A plus DS plus AD minus BC equals 0. And this now forms our second order system, which is the same as this one here. So this is the same as S squared plus 2 zeta omega ns plus omega n squared. All that term is the omega n squared. So we can then do compare coefficients to get omega n and compare coefficients to get the damping ratio. So we could do an example on this now, using these numbers here. So it's going to be the equation that we're going to go for is this one here. So it's going to be s squared minus an a plus d. So we can add this one to this one. So it's going to be 0.0933 plus minus, well, there's three minuses here, so we've got a minus and a minus and a minus. So it's going to be a plus. So it's going to be plus 0.0933 plus 0.7589 times s. And then this part here is fairly straightforward to get. It's just going to be this times this minus this times this. So again, minus times minus is a plus, minus times minus is a plus. So it's going to be plus 0.0933 times 0.7589 plus 0.1 or 0.0185 I'm not doing well here, multiplied by 169.25. So that's our parameters, and if we work those out, it comes down to s squared plus 0.842s plus 3.2 equals 0. So this expression here now is the same as this one here. So we then say that omega n squared is 3.2. So we get omega n squared is 3.2. And then omega n we get by taking the square root of 3.2, which comes out as 1.79 radians per second. And then we know this term here, that's the 0.842, that is equal to 2 zeta omega n. So we've got 2 zeta omega n is given by 0.842. And I know now what omega n is because I've got it here. So I get the damping ratio is equal to 0.842 over 2 times 1.79. So 0.842 times 2 over 1.79 comes out as 0.23. So I've now been able to extract from this original 4x4 matrix the roll mode and the Dutch roll mode. And the way we've done that is very simple. Go for this parameter here, that's the 2x2 element. That is the, with a negative sign removed, that is the pole associated with the, or the mode associated with the Dutch roll. If you want the time constant of the mode, it's 1 over the pole. If we want to get the Dutch roll mode, we have to extract those 4 numbers there, that's these 4 here, and then work out the eigenvalues of a 2x2 matrix. And we can then do the standard analysis, compare it with our standard second order system equation, and then that allows us then to extract from it omega n and then damping ratio. So in this particular case, the natural frequency for the Dutch roll mode was 1.79 radians per second and the damping ratio is 0.23. Notice the damping ratio for the Dutch roll mode is quite low, which means the plane can yaw quite a bit. So hopefully you find this useful if ever you wanted to work out the roll mode or the Dutch roll mode, natural frequency and damping ratio.